What if you have a function of, say, two variables, f of x, y, where x and y were other functions of two variables, like x of hg and y of hg?
I refuse to use U and V. I'm sorry, they're just way too similar.
This may seem a little convoluted at first, and without understanding of the chain rule first, it can get even more confusing. So make sure you start off with the basic case of the multivariable chain rule, in which x and y are just single variable functions. I strongly recommend checking out any online materials you may have or some textbook material you can find. Let's say we have a function w equals f of x, y, where x equals x of hg and y equals y of hg. So then w equals f of x of hg, y of hg. The question is, how can we find the partial derivative of w with respect to one of those fundamental variables, h or g? First, let's make a visualization to more easily understand the situation. This shows that a change in h or a change in g causes changes in x and y, which in turn cause changes in w. In other words, w depends on x and y, which depend on h and g themselves. First, let's put this in terms of differentials. We know that dw equals partial w over partial x dx plus partial w over partial y dy. We want to change dx and dy so that it goes deeper, meaning we want dx and dy in terms of h and g. It's kind of like Russian nesting dolls for a very weird analogy, as in there's one encompassing all of them, and once you unfold the layers, there's that one fundamental doll that you can't split into further dolls. And you're trying to get to the root of that, except they aren't exactly dependent on each other in the way that these variables are. So let's think to ourselves in terms of changes in these variables and how they affect the rest of the variables and the function itself. The differential dw represents the change of the whole function w. The dx and dy differentials show how x and y are changing, depending on the variables h and g. So really we want to ask, if you change h or g by some amount, how does the function w change? Let's break down dx and dy into differentials. Recall the basic formula. df equals f sub x dx plus f sub y dy for some function f of x, y. Or if you prefer, df equals partial f over partial x dx plus partial f over partial y dy. It's just a difference in notation. Similarly, we have in this case dx equals partial x over partial h dh plus partial x over partial g dg. We're just taking the total differential of the function x of hg. Just to point out, if you are not familiar with this notation, f sub x means the partial derivative of f with respect to x, and x sub h similarly means the partial derivative of the function x with respect to h. Taking the total differential of y as well, so we can rewrite dy in the original formula in terms of h and g, we have dy equals partial y over partial h dh plus partial y over partial g dg. So now substituting dx and dy with what we found earlier, we get the whole equation to be dw equals partial w over partial x, parentheses, partial x over partial h dh plus partial x over partial g dg, close parentheses, plus partial w over partial y, parentheses again, partial y over partial h dh plus partial y over partial g dg. Pretty confusing. So now we can distribute partial w over partial x and partial w over partial y, multiplying them through. Now let's rewrite this so that we can group terms by differentials. This becomes important later. So now we get dw equals partial f over partial x times partial x over partial h dh plus partial f over partial y times partial y over partial h dh plus partial f over partial x times partial x over partial g dg plus partial f over partial y times partial y over partial g dg. So then from that we can get partial f over partial x times partial x over partial h plus partial f over partial y times partial y over partial h dh plus partial f over partial x times partial x over partial g plus partial f over partial y times partial y over partial g dg. Jesus Christ. Now, finally, we can arrive at our answer, the partial derivative of w with respect to h and g. This part represents the rate of change of the function w with respect to h, g held constant, and this part represents the rate of change of w with respect to g, h held constant. Note that when h is held constant, for example, dh becomes 0. Same with dg if g is held constant, since there is no change in the variable, and the differential represents a small change. So we're effectively erasing that term, and we're free to divide dw by the remaining differential and get the rate of change with respect to that variable. So now let's rewrite, dividing by dh. And here's a version written in the other notation, which in my opinion makes a bit more sense. I'll explain this term by term. I'll just do it for h since the same thing applies to the g version as well. W is the most dependent variable here, depending on x and y, which depend on h and g. H is the independent variable. It is not a function of anything. So partial w over partial h is sort of the rate of change of the most dependent variable with respect to the independent one. Partial w over partial h shows how the function depends on the fundamental variable h. Partial w over partial x and partial w over partial y shows how w depends on x or y, or in other words, the rate of change of w with respect to x or y. Partial x over partial h and partial y over partial h shows how x and y depend on h. So overall, you're getting the relationship between sort of the most dependent variable with the independent variable through analyzing the relationships of the variables going down the dependence chart. In a bit of a clearer sense, if you think about changing h slightly, just a bit, that translates into a simultaneous change in x and y. And then those changes added together cause a change in w, since w depends on x and y. Same thing goes for g.